Good morning. So I will be talking about LLVM IR a bit, in particular about some changes that have happened in the recent past and changes I expect to see in the, well, near-ish future. But to start with, I want to look at the very distant past, so all the way back to LLVM 1.0. I basically picked out a random test from the repository at that time. It doesn't do all that much, it just allocates some memory, stores into it, and frees it again. But I'm kind of curious who in the audience was involved with the LLVM project when the IR looked like this. Okay, I see one hand here. Two more. Okay, that's not a lot of people, but respect. That's a very long time, long before my time. I mean, this looks pretty familiar. It does have some unusual elements. For example, we have this implementation begin and stuff. We have the C-style integer types, so long and uint and things like that. And we also had first-class malloc and free instructions. Then over time, those things all went away. So in 2.0, we already have more familiar syntax, and we have the signless integer types. Then 2.7 dropped first-class malloc free. Instead, we have normal function calls. And then the last change was LLVM 15, the switch to opaque pointers. And at that point, we have reached LLVM IR like it looks like today. So one of the common threads here is what I would call the de-type-ification, so the removal of unnecessary type information from the IR. The two examples here are the signless integer type, so instead of having a signed and an unsigned type, we have a single integer type. And similarly, instead of having lots of different pointer types, we have a single opaque pointer type. And the motivation for these changes is basically always the same. So we avoid introducing bitcasts, and, well, it does not strictly enable any new optimizations, but it certainly guides us in a more general direction. So for example, if your signed add and your unsigned add are literally the same operation, it becomes a lot simpler to deduplicate them. Like, you don't have to do anything special, it basically comes for free. And there is also a correctness aspect here, because if you give people a pointer type and you tell them a pointer type with an element type, and you tell them you are not allowed to use that element type because it has no semantics. Like, what's going to happen? I mean, the type is right there, so of course people are going to use it. The only way to actually prevent that is to remove it. So this is the past. One of the ongoing changes in the same direction is the migration from the get element pointer to the pointer add instruction. So here we have, the way it currently works is get element pointer is type-based. So you have a base type, and you have indexes into that type. And here we have 3 different get element pointer instructions, which all do exactly the same thing, which is to add 4 bytes to a pointer. And the goal is to change the representation to a single pointer add instruction that does no more and no less than add an offset to a pointer. This is partially complete, so we are currently using get element pointer I8 if we can, which is basically the same as a pointer add instruction. What has not happened yet is doing this for variable offsets. That case is a bit more tricky because we usually have a scaling factor. And this scaling factor could either be represented as a dedicated shift or multiply instruction, or it could be folded into the pointer add itself as a native scaling support. And the decision on which direction to go is kind of still outstanding. And this is where this particular project is stuck right now, basically. So this is not the only place. If we look further, for example, we have alloc A instructions, which currently take a type. But the only thing you are allowed to use from that type is its size and alignment. So ideally, we would directly represent it as such, which also prevents people from making silly mistakes like looking at that type, seeing there are 4 padding bytes in the middle and thinking like I can ignore those 4 bytes for optimization purposes, which is a natural assumption to make, but also entirely wrong. Same argument goes for various attributes like bival, sret, and to a more limited degree also for global variables. But those are trickier because they also have initializers. So this is one of the general directions we are going. From here, let me switch to a completely different topic, which is the fact that we have added a lot of new instruction flags in the last couple of LLVM versions. So we have things like or disjoint, zero extent non-negative, or truncate without unsigned wrap. And one thing a lot of the new flags are targeting is the ability to undo canonicalization transforms. So for example, an or disjoint instruction can be converted back into an add. Zero extent non-negative into sign extent, or a same sign comparison can switch between unsigned and signed predicates transparently. So to give an example, if we shift the value by 2 bits, we know the low 2 bits are 0. And if we add 1, we can convert that add into an or. We do that both like as a general principle to reduce the number of different IR representations, but also because ORs are just simpler to analyze. They have very predictable bit propagation patterns. However, sometimes we just prefer adds instead of ORs. For example, if you are matching an addressing mode, if you want to form a LIA instruction on x86, then like addressing modes allow you to embed a small constant offset into a memory instruction, but they don't allow you to embed a small constant OR. So we have to undo the transform. And in this simple example, we can just do it based on local analysis, but in more complex examples, having the flag allows us to do this reliably, even if the original transform used some kind of, I don't know, control flow or interprocedural analysis. So this is like part of the motivation here. The other part is generally for instruction flags, the ability to manifest analysis results and enable cooperation across passes. So we can have one pass that, for example, does some kind of sophisticated interprocedural analysis to infer the instruction flags, and then have a second pass that just does local transforms based on the flags. And finally, it also enables us to convey guarantees from the front end, so based on language semantics. In which case, these are facts that LLVM might not be capable of inferring itself, but which we know based on front-end semantics. So this particular point is something I want to discuss in a bit more detail. So this point of manifesting analysis results in the IR, or more generally, value constraints in the IR. Because this is, I think, generally a core problem of optimizing compilers, and something where LLVM offers a lot of different mechanisms, even though we are not really happy with any of them. So we have attributes and metadata, which allow fairly precise information, like precise value ranges, but they effectively only operate at call or load boundaries, which also means they are very easily lost. Like if you inline a call, the attributes on that call are lost forever. We have instruction flags, which are a lot less precise. So for example, you have the non-negative flag, which just gives you a single bit of information instead of a full range. And they only apply to, specific flags only apply to specific instructions. And we have assumptions, which are like the fully general mechanism, so you can encode anything in an assumption, but they often also negatively impact optimization, because you have the assumptions in the instruction stream and you have additional uses, and both of those act as optimization blockers. So yeah, this is kind of remains a somewhat unsolved problem, and our current strategy is to just keep adding more attributes, flags, and so on, in the hope that things will get better. So one thought that has crossed my mind is that for some of these new flags, they don't really have anything to do with the surrounding instruction. They are pure statements about the value. And it really would make more sense to not have something like a zero extent non-negative instruction, and instead have a normal zero extent that has a non-negative operand. So flags at the use sites, a specific operands. Like this generalizes, so this would subsume a bunch of the recently added instruction flags, like the one on UI to FP. The same sign comparison is basically the same. And also flags we currently don't have. Like we don't have a logical shift right non-negative, even though it would actually be quite useful. The generalization of that will be to have range information at specific uses or operands. Now, this is, I mean, nice concept, but there are some big problems. And generally, one of the biggest problems we have is that every single time we add new instruction flags, we get a whole bunch of new miscompilations. And the main cause of that is that there are lots of transforms that modify instructions in place, and those modifications may not uphold the invariance of the new flags, which is why we generally recommend that transforms create new instructions instead of modifying existing ones. But a lot of them don't. And of course, we have the problem that there is a lot of overhead for storing information about individual uses. Though there are some trade-offs we can make. For example, if we just store the number of leading 0 bits, that gives us like most of the optimization benefit for a lot less cost. But anyway, this is a very speculative direction. I'm not really convinced whether it makes sense or not. So let me get a bit back down to earth and switch to the next topic, which is next to a lot of new instruction flags, we also have a lot of new attributes with essentially the same motivation. So convey front-end constraints and manifest analysis results. The only one I'm going to discuss in more detail here is the newest one, which is the captures attribute. So captures replaces the old no capture. So no capture is captures none. And what is new here is that captures allows you to specify which components of the pointer are potentially captured. And the main components are the address and the provenance. So we can say this pointer argument only captures the address of the pointer, but not its provenance. Or we can say it captures both, but only through the function return value. And the key question here is, what does that mean? So address is the information about the integral value of the pointer or the pointer identity, while provenance is the actual permission to do memory accesses through that pointer. Because we have this notion of provenance, just because you know the address of a memory object does not mean you're actually allowed to use it. You have to have the corresponding provenance. This is an important distinction. For example, alias analysis and memory optimization in general, they don't care about addresses at all. They only care about provenance. That also means, for example, pointer comparisons, which only look at the address but don't expose the provenance, they now no longer interfere with alias analysis and memory optimization. So the reason why I'm highlighting this topic is that it's part of a larger goal. And the broader context here is that if you look at the pointer to int instruction, so you're converting a pointer to an integer, and then you want to convert the integer back to a pointer. What happens here is that the pointer to integer conversion exposes the provenance of the pointer, and which can then be recovered when you convert the integer back to pointer. Otherwise, you wouldn't really be able to use the resulting pointer for anything useful. The problem here is that this technically makes pointer to int a side effect. And this means we are not allowed to eliminate that pointer to int instructions. We do it anyway, even though it causes miscompilations. We do it anyway because otherwise the optimization impact would just be way too high. And part of the problem is that LLVM currently has no mechanism at all to give you a pointer address without also exposing the provenance at the same time. So we need a mechanism to do that. So for example, a flag on pointer to int, or possibly a separate like pointer to address instruction, which may be useful for some unrelated reasons as well. And closely related to that, one of the biggest contributors of pointer to int instructions in the IR is pointer subtraction, because LLVM does not have a native operation for that. So you have to first convert to integers and then subtract as integers. Which means every time you subtract pointers, you also expose the provenance, which means to have a pointer escape, which means most memory optimization stops working. So I think we should have like a dedicated pointer sub instruction to mirror the pointer add, which would only capture the address. And if we combine that with the like usual flags, for example, in C, if you subtract pointers, they are required to be part of the same memory object. So in that case, actually, the subtraction does not leak any information about the base address of the object. So the general direction here is basically more explicitly tracking provenance exposure and reducing the amount of times it happens so that we can, in the future, hopefully address existing miscompilations affecting, like related to pointer to integer conversions. So this is all, basically. Just to summarize, the three topics I covered was the de-type-ification agenda. The second is the like how we manifest analysis results and constraints in the IR. And the third one is reducing pointer provenance exposure in LLVM IR and generally taking provenance more seriously with a goal to reduce, to fix miscompilations while improving optimization along the way. Like I should say, this is, of course, by far not everything going on in terms of IR changes. There are lots of other things. For example, recent really amazing work to switch debug info representation from intrinsics to records. And there are more upcoming changes to improve debug location handling. Then there is also an upcoming major change to how we represent constrained FP, so from specialized intrinsics to operand bundles on generic intrinsics, and lots of other stuff that, I already saw the 1 minute mark just now, so I don't have time to cover. So let me close here. So thanks for your attention, and if you have questions, I would be happy to answer them.
Hi, so I have a question about the constraint stuff. Would it make sense if we start already implementing and using some generic API for invalidating certain constraints? Because right now, like if you, for example, change an instruction in place, you just, I think, nuke all the flags most of the time just to be safe, like the UB implying flags on certain values. Would it make sense to start having like a generic API as in, remove all flags that, I don't know, somehow correlate with some predicate to whatever we just changed? And then with the idea that later on, once there's like a final system for constraint tracking in the IR, that this would essentially move in automatically.
Yeah, we already have a lot of generic APIs. Like a typical one is things like drop Poisson generating flags or drop UB implying attributes, which you can use depending on the situation. I guess the problem always is you have to actually remember to call those.
I guess my point is, instead of just dropping all flags that imply UB or whatever, it's more like drop all flags with all flags, and then you provide some kind of predicate that says this is what I changed, so that later on, if we add like new flags, it doesn't just drop all of them. Like let's say you only change the sign bit or whatever, and then you kind of encode this into the generic API. That later on, if you have a more fine-grained tracking system, it would automatically only drop the relevant flags and not just nuke the whole thing, essentially.
Yeah, generally it makes sense if you can like find a good trade-off between describing the change you made while keeping it kind of still generic enough to be useful. Then I would say yes, that makes sense. I don't know if that's actually possible in practice or not.
Okay, thanks.
Hi. So a couple of years ago, there was a talk about comparing and contrasting LLVM IR to MLIR, and it had some suggestions on how they could be unified, and nothing has, as far as I'm aware, happened in that direction since then. Is that something that we should be spending some time on, or is that best left lying there?
Yeah, I mean that's a very good question. The thing to always kind of keep in mind is that it is incredibly hard to make LLVM IR changes. Like if you have gone through the process of doing a major IR change, then you kind of feel like you never want to do that again. Just because like we have huge amounts of code both in LLVM and outside that has to be updated. So like doing any kind of radical change is just very hard. Like there are definitely things about MLIR I think we should consider adopting in LLVM, but there's always a question of what the cost of actually doing that is going to be. Like I like the idea of basic block arguments instead of phi nodes, but I'm scared of implementing it.
Okay, so you said anyone that has done a change realizes how much work it is and doesn't want to do it again. Do you think that's a good thing or a bad thing, or?
Well, kind of both. I mean, we shouldn't just be doing changes randomly because doing changes has real costs on other people. But we should also not shy away from it. I think like generally a great strength of the LLVM community is that like changes are never rejected as long as someone is really willing to do the work. Often no one is, but if you're willing to do it, then like there is like no fundamental inertia that says, no, we just are not going to do that.
Yeah. Well, no one here.
But I definitely know that, like for example, the OPEC pointers migration has been painful for a lot of people.
I think that was one of the biggest, yeah.
Yes.
Do you have, I mean, on the MLIR node of things we might want to adopt, do you have any thoughts on heterogeneous LLVM IR modules that have more than one data layout, more than one target triple?
Yeah, that's a pretty tricky question. I don't have any specific thoughts. Like I would say we already have quite some trouble getting the data layout into all the places it is needed. Like for example, especially when it comes to constants, which kind of live outside the module and as such don't have access to the data layout. Yeah, to be honest,
Okay.
like off the cuff, I can't really.
Okay, fair.
I'd have to think more about that one.
Thank you.